Well, greetings from the American Segmental Bridge Institute. I'm Greg Freeby, the Executive Director of ASBI, and would like to welcome you to our monthly webinar. We have a great program for you today. Just some quick announcements before. I want to ensure that you all are following the American Segmental Bridge Institute on LinkedIn. You can follow me as well. Certainly following ASBI's page on LinkedIn, you'll stay current on some of the most up-to-date information about events and other things going on in the segmental and complex concrete bridge arena. Hopefully you all are here today to see presentation by Mr. Kent Montgomery with GM2 Associates on preliminary design approximations for segmental bridges. And again, some quick announcements. If you registered for this webinar, hopefully you did so through the QR code you see on screen, which means you got pre-registered for all of our webinars for the year. If you signed up for this one individually, you can certainly continue to do that option, but we'd encourage you to do the single sign up option, which will let you be pre-registered then for all of our webinars this year. You'll get a notice by email. You'll have an opportunity in that email to create a calendar appointment, and that way you can stay up and current and not have to remember each month to register for the webinar. A little plugs for some resources that are available in the concrete bridge community. This is the Resources for Concrete Bridge Design and Construction document published by AASHTO in collaboration with the National Concrete Bridge Council, of which ASBI is a member. You'll see a number of resources in there relating to segmental bridges and other concrete bridge topics. So we'd encourage you to seek out that resource. Again, it's free as a digital download from AASHTO. It was published just about a year ago. Also encourage you to attend our July webinar on the last Wednesday of the month of July. July 30th at 1 o'clock Eastern. We'll have the folks from Kiewit make a presentation about a unique project where they used segmental bridging to span a landslide in a really complicated design and construction site. So it's a great opportunity to further your knowledge on the use of segmental. Some quick instructions on the use of our webinar tool today. And some just important notes. If you lose a connection during the webinar, you can rejoin with the link. You're certainly going to miss content while you're away. We need you to attend as close to an hour of content today in order to be eligible for an attendance certificate, which again is the next bullet point. We're going to issue those to everybody who attends the minimum amount of time in the session, but do allow about a week for your attendance certificate to arrive via email. And then we'll be doing Q&A at the end of the session today. And the way this will work, because we have so many attendees, you have an opportunity in the go-to dialogue pane to type in your questions at any time. And hopefully you all are seeing my slides go. I'm hearing somebody say the slides are paused, and that is absolutely correct. So apologies for that I'm speaking without slides moving forward. So sorry about that. Let me just jump in, and you should now be seeing live slides. And I'll just go through quickly, again, just visually let you see the content that unfortunately had paused. Here's the QR code that I mentioned about for signing up for the monthly webinars. You have an opportunity to do a screenshot of that. Go ahead.
Hi, Greg. Hey, it's still not advancing on my screen. I'm just seeing the webinar will begin soon graphic.
No, let's see about that then. Thank you for that. Let me stop. All right. You should now be seeing my screen. Showing the monthly webinars.
Nothing yet for me.
Okay, some folks are saying they see it now
Okay.
I see it.
and that they rejoin. You're seeing the monthly webinars slide?
Yes.
Okay. Again, folks, apologies. You know, we do these test sessions, but sometimes things don't work as planned. So again, the slides, and I'll make these slides available too, since there were some QR codes available. We'll post those up on our website after the session in a PDF format so that you'll get the content that you've kind of missed here as far as the visuals. Again, I mentioned this construction practice or a resources document for bridge design and construction from the AASHTO website. And again, the July webinar with the folks from Kiewit. And then we'll hop into the webinar instructions. If you're on a desktop computer, you should in your dialog have a little pull down that says questions, where you would be able to type in your questions. And I've seen a few of them already come up from folks saying, hey, can't see your screen. So hopefully that has remedied itself, or we've taken care of that. And then if you're on a mobile device, you can also hit the little question marks pane or dialogue to be able to type in your questions. Our Q&A moderator that you just kind of heard from a bit ago, Wade Bonzen, is the chair of our ASBI Construction Practices Work Group. He's going to be leading the group through a moderated Q&A. He's the project development manager for complex bridges at GM2 Associates. And it just so happens our speaker today is also an employee of GM2 Associates, Mr. Kent Montgomery. And I'll introduce him, and then I'll turn over the sharing to him, and he'll take us through his presentation, and hopefully he won't have the challenges that I just did. Kent holds a BS and MS from the University of Colorado with an emphasis in structural engineering in both of those degrees. He's been a member of ASBI since 1993 and is currently the chair of the ASBI Design Subcommittee. And I say currently, but Kent is actually retiring and has turned over that chairmanship almost as we speak. And we're certainly going to miss him in that role. And in that role, he has also provided enormous support to the AASHTO Concrete Committee, not just on things segmental, certainly that's been our focus, but also kind of on all things concrete, because Kent has a number of years of experience, holds a lot of institutional knowledge, and has, unlike some of us, he's able to recall a lot of that knowledge and find things that a lot of us can't find. Kent has worked on design and construction for over 24 major segmental bridges, including the Wabasha Bridge in Minnesota, the Hanging Lake Viaduct in Colorado, the Sailboat Bridge in Oklahoma, I-35W Bridge, the Four Bears Bridge in North Dakota, and a number of others. I couldn't begin to list them all. So with that, I'm going to turn over to Kent and let him hopefully share his presentation. And again, apologies for the little burble on my part.
Okay, hopefully everyone can see this. As Greg mentioned, my presentation is going to be on preliminary design approximations, specifically segmental proportioning for cross sections and span layouts. This presentation will closely follow two articles that appeared recently in Aspire magazine for concrete bridge technology. And just to let you know, there will be two more articles coming up in the near future that extend on these concepts. And these first two articles are available in the go-to handout section. The requisite continuing engineering slide. And this seminar will explain how to determine concrete segmental box girder dimensions to satisfy both longitudinal and transverse design requirements. Includes setting structure depths, the intratus profile if it's variable depth, top slab, bottom slab, web dimensions, and touches upon how constructability and practicality influence the selected dimensions. And at the end of this seminar, hopefully, you'll be able to explain the need for a good preliminary design, determine the structure depths and intratus profiles, describe how to determine the top slab, bottom slab, and web dimensions, and explain how constructability and practicality influence the selected dimensions. This presentation targets conceptual and preliminary design, a good starting point. I will point out that a good starting point results in a more optimized design, as can be visualized in this minima surface. You start in the wrong point at final design and do a little bit of iteration. You might find a local minimum, but you might not have the true optimized design. Obviously, when you are done setting all your dimensions and everything, you'll need to confirm your cross-section during final design with a full final design analysis, including a time-dependent analysis, verify your flexural stresses, your flexural strength, shear strength, and so on. And I will note that a good section development in preliminary design results in few or no changes during final design, using some of the rules of thumb presented in this presentation. Have resulted in final design efforts that have very few changes, no backing up, which affects not only your longitudinal designer, but then your transverse designer and so on. So it really helps with schedule and with budget to have a good preliminary design. We will touch upon the longitudinal behavior, the transverse behavior, substructure considerations, constructability, and a little bit on aesthetics. Now, when focusing in on your preliminary design, you can't consider one aspect, for instance, longitudinal to the exclusion of all others, or you're going to be doing a lot of backing up. You need to work each one of those shown, constructability, transverse, longitudinal, and so on, together to bring them in to a final optimum solution. Now getting on to longitudinal behavior, we'll talk about span to depth ratios and depth profiles, web thicknesses, bottom slab thicknesses, and some practical considerations. Constant depth structures, this presentation is going to target span by span and balanced cantilever. I'm not going to get into cable stay bridges, but with span by span construction, span to depth ratio of 16 to 22 usually works very well, with 18 being optimal. And for balanced cantilever construction, I'm going to say up to about a 250-foot span before you start wanting to go to true variable depth structures. And the span to depth ratio is a little thinner, 18 to 22, with 20 being optimal. I will note that, especially on the upper range of these spans, you're probably going to need to thicken the bottom slab. And I'll pause for a moment in this slide to say there's going to be, some recommendations shown, for instance, a span ratio of 18 to 22 or a 250-foot span. That's not to say that thinner or thicker span to depth ratios haven't been utilized successfully, or that the longer span has been done with a constant depth structure and balanced cantilever. But if you stick to these limits, you'll typically have a pretty good final design effort. Mentioned you need to thicken the bottom slab for balanced cantilever. There's two ways to achieve this. One is to thicken the bottom slab to the inside. This will require a modification of the core form and bulkhead. We'll touch upon those terms a little bit later in the presentation in more detail, but two aspects of casting form need to be modified. It's not structurally efficient. You have a higher web shear. The inclined compressive stresses in the bottom slab, inclined upward, actually serve to increase the web shear that you need to account for in final design in this situation. And it does decrease the effective depth if you think of the couple between the top slab, post-tensioning tendons and the centroid of the compression in the bottom slab. The other option is to thicken to the outside. Of course, we get nitpicky. It's not a true variable depth, or it's not true constant depth. It has a little bit of variable depth, but it's usually not noticeable, and we haven't gone to the extent of a true variable depth structure. We're just thickening the bottom slab a little to the outside. This requires changes to the soffit table and the bulkhead. Again, we'll touch upon those a little more, but two aspects of casting form, so about as equally easy to achieve. It is more structurally efficient. It obviously increases the effective depth, and it does not increase the web sheet. In fact, in this case, the compression stress in the bottom slab is angled downward, which gives you a small positive result or arching effect. Typically in these cases, it's pretty small. You can ignore it or account for it for a little bit more optimization. Moving on to true variable depth structures. Again, as we push spans above about 250 feet up to these have pushed up as long as 750 feet, maybe longer. The depth at the pier is the same as for constant depth, 18 to 22, with 20 being optimal. But we like to thin it up as we move to mid-span. We don't like all that concrete hanging out there in the cantilever state, or really in the continuous state also. So the span to depth ratio at mid-span would be 35 to 50, about 45 being optimal, I believe. I like to thin it up as much as reasonable. If you go beyond 50, you can have some unintended consequences with geometry control. It gets very flexible, as well as negative aspects that could occur if your creep is somewhat more than you analyzed for. One caveat is that you really don't want to go deeper or shallower than 7 feet at mid-span. And the reason for this is that you need to have access inside that box during construction. And if you're at 7 feet, you're probably already less than 6 feet inside the box, but you need to get in there to stress your continuity tendons, whether they be bottom slab or drape tendons. And in the long term, we like to have low maintenance and high inspectability on our bridges. And we want the owner's inspectors to be able to get in there without, crawling around too much and get a good inspection of the bridge. So we know the depth at the pier, we know the depth at mid-span. So what is the profile in between? And an easy way to achieve this is to set your X ordinate at mid-span, moving towards the pier. In practicality, it's probably going to be starting at the end of your first typical segment at the tip of the cantilever and not be in the closure or anything. But those are details you can work out. And use this exponent type equation that we can see here. The exponent's on the X ordinate, and obviously if it's 0, you have a constant depth structure. If it's 1, you have a linear haunch, which again, not very optimized, a lot of concrete hanging out there, and like to thin it up a little more. The exponent goes to 2, you're at a true parabola. And in my experience, you'll find that there will be a weak point somewhere along the quarter point of the span, and then that area will govern other aspects of the design specifically that you have to overcome. And we like to have our bridges pretty much be governed equally along the length of the bridge. 1.7 to 1.9 is typically a good exponent to use, with I believe 1.8 being about optimal. You can solve for that constant then, given the exponent, the half span length, and the depths at pier and mid-span. Sometimes you'll cheat up to the high range if you're trying to work with nav clearances or something like that, but wouldn't really recommend going more than 1.9 on the exponent. Bottom slab thickness profile. Balanced cantilever bridges are going to be thicker at the pier, even in a true variable depth structure. And I recommend using the same equation and exponent, so the same form of the equation, but you're going to transition from the maximum thickness at the pier We'll touch upon that in a little bit, how to determine that. And to the minimum thickness, over approximately 60% of the cantilever length, obviously compute a new equation constant C, and you have it worked out at every joint. Again, we're really only interested in the overall depth and the thickness at joints, which is where it's going to be determined both in precast and cast in place. It'll be corded between the joints, but typically you can't really notice that. As you can see in the Monongahela River Bridge here, results in a nice curve. Web thickness, now getting into the individual components of or elements of the cross section. I recommend a web area of between 0.36 and 0.39 inches squared per square foot of span deck area. This is based upon a notional vertical web, so we don't need to get involved in the inclines and so on. For example, a 316-foot span, 53-foot wide box, 16 foot 6 inches deep at the pier. You run through the ratio, and you get a total web width of about 30.5 inches. That results in one web about 15.25 inches. So we can say about 1 foot 3 inches. A little bit of note on setting these dimensions, we went on the low side here. And if you do, you need to realize that you may need to back up in final design just a little bit. So you need to have a schedule and budget to accommodate that. If you're, for instance, in an emergency replacement and schedule is everything and there's no room to back up, and you want to err on the high side of these ratios, just to be sure that it's going to work in final design. Should we use variable thickness webs? Should we use variable thickness webs? I recommend a constant web thickness for variable depth structures. As you get true variable depth, you have to hold sort of a minimum web width at the bottom, and therefore the thickness doesn't really change that much for the majority of your segments. It just gets kind of unwieldy, so I don't really recommend using it for variable depth structures. I've most often seen it in span-by-span bridges with constant depth. You can thin it up at the bottom because the live load moments that are kicked into the webs because of live load on the deck and the monolithic connection pretty much go to zero at the bottom of the web. So you're only handling shear and torsion at the bottom, while at the top you got to make additive shear, torsion, and bending requirements. If variable thickness is utilized, remember to utilize the minimum thickness in the strength calculations if you're using modified compression field theory. Bottom slab thickness for span by span. If you did a optimization for just longitudinal bending, it would pretty much result in no bottom slab. But recommend having a minimum bottom slab of 7 inches to preserve the closed box section, which we like for a number of reasons. One is that it's very torsionally rigid and provides a lot of torsional resistance for eccentric loads, especially if there's a curve on the bridge. And the other reason is the theory of segmental geometry control. We're basically considering each segment a rigid body that is going through rotations in the match cast position and in erection and so on. And you're not going to really have a nice rigid body if you don't preserve that closed box cross section. A word that we should not exceed a bottom slab width to thickness ratio of 35. Oops. And we will touch upon that in just a little bit more. Bottom slab thickness for balanced cantilever, the minimum near mid-span is determined by the continuity tendon duct size, bottom slab tendons, typically a little over 8 inches for 12 strand, 0.6 inch diameter strand tendons, or closer to 9 inches for 19K6 tendons, but obviously it depends upon the clear cover requirements of the owner. And you can work that out. It's pretty simple geometrics with the clear cover, the reinforcing that has to be in there, and the ducts. At the pier, recommend an initial sizing of 9 inches thick for every 100 feet of span. Basically, for instance, 250-foot span would be 22 inches thick at the pier. Next step in preliminary design is to check the stresses to make sure that preliminary sizing of 9 inches for every 100 feet is good. So you check the stresses in the cantilever state, including construction loads, to size cantilever post tensioning and check concrete compression. Excuse me. A note on this is that if you have significant construction loads, for instance, a form traveler or a beam and winch, pretty much the cantilever state's going to govern the stress, the negative stresses and the compression. I'm sorry, the compression stresses and the tension stresses in the cantilever state, and not the in-service condition. If you don't have any significant construction loads, for instance, just the 10 PSF distributed construction live load, then it's going to be sort of a toss-up, but they're both going to be very close to governing the same. And if you size it in cantilever state, you should be okay in the in-service condition. Recommend targeting 0 tension for precast structures and 3 square root tension for cast-in-place structures with continuous bonded reinforcing. The LRP specifications will let you go up to much higher levels of tension. And if you do that, there's probably a good likelihood that there's going to be a crack or a joint opening in the precast sense. And that tends to get people very concerned and very upset. And we just want people to have good confidence in their bridge, even though that we know in the final condition those cracks will close up. So recommend using a little bit lower tension, just so everyone feels very good about their structure. I recommend a maximum compression in the balanced cantilever state of 0.55 F prime C, a little bit lower than it's allowed. One of the reasons for this is that it will help minimize the amount of moment redistribution due to creep and shrinkage. The actual redistribution mechanism is a topic sort of beyond this presentation, but it does occur. And if you minimize it a little, you can help control that redistribution, which really helps quite a bit with the continuity post-tension design. There is a FEW term listed here, and we will get into that at this point here. This is in the LRFD specifications. Then you have that bottom slab to thickness ratio that is termed phi or lambda W. If lambda is less than 15, then you basically don't have to worry about it. Or PW becomes 1. If it's between 15 and 25, it transitions from 1 to 0.75. And between 25 and 35, it's 0.75. And the code says beyond that, you need to study it in more detail. I just recommend not approaching that 35 limit, sticking somewhere between 25 and 35, preferably closer to the 25. Then your compression allowable becomes FEW 0.6 F prime C, just to keep that in mind when you're sizing your bottom slab and checking compression. That FEW term also comes into being in checking your flexural capacity at the strength limit state. Finally, check the bottom slab thickness for the strength behavior. You can do this very quickly by just assuming all the internal post-tensioning is at 95% of guts, your cantilever post-tensioning. It's going to be pretty darn close for a balanced cantilever bridge with quite a few cantilever tendons in there. Maybe a little bit on the low side, but that's good for preliminary design. If you have any external tendons, not typical in balanced cantilever design, they would be at 90% of guts in the strength limit state. Then you compute the compression block and the location of the neutral axis just by balancing equilibrium. And you check that the bottom slab thickness is not less than the neutral axis location C. If it's a little over, not a big deal, but we don't like our neutral axis location to climb up the webs, primarily because this results in a transition from a tension failure to a compression failure. And we like ductile structures. We want our structures to perform ductilely and not be governed by compression failures. Practically speaking, as you transition from a tension failure to a compression failure, your fee factor transitions to 0.75, so you can take a hit on your nominal moment capacity, and can make it challenging to make the strength limit state work. Practical considerations: we must be able to fit all the required post-tensioning. Notice we haven't talked about the top slab yet. That's primarily governed by transverse behavior, so we'll touch upon that in a moment. But one aspect is we must be able to fit all the post-tensioning in there. If we have anchors that are located in the cross-section, you have to make sure they fit in that knuckle region there. You have to make sure you can fit all your tendons in the top slab as well as the bottom slab, as you can see in this simple study drawing. And if we're in a precast situation, we could use epoxy squeeze either from external tendons, in which case it doesn't matter, bar tendons, or internal tendons that become permanent, internal bar tendons, as you can see here, in which case you have to fit those ducts in, as well as the anchor plate. A little bit on practical considerations. I'll use the Saginaw Bridge and Bath, Maine for this. The 184-foot approach spans utilized a constant 9-foot structure depth. Therefore, we set the mid-span of the main river unit for all spans at 9 feet to match, because aesthetics was very important to this community. We sort of split the difference. It resulted in a span to depth ratio of 47 for the 420-foot main span, and 36 for the 331-foot river spans. Slightly high and slightly low from optimal, but you're splitting the difference, making it all work together. In the final selection of the segments and the Intrados profile, we developed one that worked in all situations. It was just truncated. So for the typical cantilever on the 330-foot, 31-foot approach spans, you had 19 segments that had a certain profile, both in the bottom slab thickness and the overall depth. When we got to the main cantilever, the segments out at the tip, those first 19 segments were exactly the same. And then we just added 5 additional segments as you went towards the pier. And that provided a compromise, required a compromise in the optimized Intrados profile, but it helped quite a bit minimize changes to the casting cell, just more pieces, or less pieces, I should say, for the casting cell, which helped save a little bit of cost there. But more importantly, the workers got into the groove of repetition and only had to modify the last 5 segments, which helped quite a bit with constructability. So a little bit of a compromise in optimizing materials to optimize the amount of labor required to build the segments. So that was longitudinal behavior. We'll now touch upon transverse behavior. We'll talk about the deck span ratio, element thicknesses, again, for transverse behavior, haunch lengths, and soffit width. By deck span ratio, what I'm referring to is the ratio of the cantilever wing length to the interior span. For initial sizing, you use 1.5 to 2 feet for that knuckle region, and then set your ratios off of that. Ratios between 0.3 and 0.55 cantilever wing length to interior span work really well. I will say that 0.42 is optimal for transverse design only, meaning that if your cantilever wing versus your interior span are going to be close to equally governing and not one over the other. Remember, we got to think about other considerations, longitudinal, especially substructure considerations. Sometimes we want to lengthen that cantilever out to about 0.55 works fairly simply. The lower ratios can be utilized if you have variable width and you're at one of your extremes of about 0.3. It also works very well if you have 2 boxes coming together in a gore area for the exterior cantilever. Sometimes I've seen very, very short cantilevers that are going to be linked with the other box in a closure pore, and that's okay to make those very short to make the geometry work out, as long as your interior span is a total interior span is a reasonable length. Element thicknesses in the top slab, recommend a minimum of 8 inches for your interior slab dimension, getting slightly thicker as we get to wider boxes over 40 feet. And you see this equation, a good approximation for how much you need to thicken it. Over the webs, 13 inches for your narrower boxes. And as they get wider, you can start thickening that up for structural reasons. Remember, this is for transverse behavior only, and we need to be fitting post-tensioning hardware up there, most likely in a cantilever state. And so sometimes that 13 inches just isn't going to cut it for a balanced cantilever bridge. But this is just for transverse behavior, and you need to look at fitting your hardware in there, as we mentioned before. 9 inches at the wingtip. This is actually in the LRFD specifications, and that is to accommodate safely the transverse post-tensioning anchors. So we need to provide at least 9 inches. I will mention that's for some narrower boxes. For instance, a single track LRT box, you might not be using transverse post-tensioning. It might work out just fine with reinforcing, in which case we don't need to worry about that minimum wingtip dimension of 9 inches, and you can make it 8 inches to match the interior. Web thickness, minimum web thickness, I recommend about 10 inches. Again, there's going to be live load on the top deck that's going to kick moments down into your webs. And if it gets too thin, for instance, for just longitudinal behavior, those moments are going to put a lot of demand, and you're going to end up requiring a lot of bending reinforcing that then is additive in certain proportions with your shear and torsion reinforcing, and it can get out of hand in a hurry. So recommend a minimum of 10 inches and getting slightly thicker with this equation, as your box gets wider. Just to point out that we're talking about the maximum that we determined for longitudinal transfers. It's not additive. So if we went back and used that equation for the longitudinal to determine the web width, and then we looked at the minimum here, it's going to be the maximum of those two, not adding the two together and get way too thick. Again, 7 inches minimum on the bottom slab. It's covered by longitudinal behavior. We talked about some of the constraints with that, including that bottom slab span to thickness ratio. Haunch lengths. Out on the wingtip, there will be typically a constant depth portion. I don't like to extend that constant depth portion beyond a cantilever length to thickness ratio of 10. If not, you'll start having a governing point for your cantilever at the end of the haunch there, at the beginning of the constant depth thickness, and that will govern over other places in your box. And again, we like areas to govern equally, not be governed by one strange point on the cross section. The haunches to the interior, typically you can set it about 0.2 minimum, very close to the counter flexure point, or as required to fit longitudinal ducts. That 0.2 is pretty short, might work out somewhere between 0.2 and 0.25 or so for a span-by-span bridge where there's no ducts on the top. But if you have cantilever tendons, it's probably going to be much, much longer and completely governed by fitting all your post-tensioning into the top flange, the deck. Soffit width, remember that in a precast situation, and sometimes in a cast in place as well, we're going to have bearings, and we don't want bearing up. And the bearings are going to be located inboard quite a bit. The center line of the bearing might be 2.5, 3.5 feet in from the soffit corner, so the ratio gets smaller even still. So unless you do a very detailed analysis in preliminary design, if you limit it to WR4 or 10-foot minimum, you should not have issues with uplift. We'll note that if you have monolithic connections, obviously, if you calculate tension region just due to the eccentric loads on one part of the pier, will require additional reinforcing, of course, but it can be fit in and go up through the into the superstructure, and not nearly as important as is for a bearing situation. Web slope, I like to limit it to 64 horizontal to 100 vertical. Gives you a reasonable design that's going to behave well. I've seen steeper slopes up to 1:1 or 100 to 100. Most of the time that I've seen it occurring on cable stayed bridges and not so much on span by span and balance cantilever. So I like to stick to this ratio here. Touch upon briefly substructure considerations. After sizing the piers and the foundations, the challenge can be focusing the loads from the deck and all your live load down into the substructure, especially for very wide boxes, 3-web boxes and so on. And so many times we're trying to minimize the pier and the foundation size, especially if it's out in a river, and we're trying to minimize the cofferdam size. The cofferdams are very expensive components, and so we're trying to minimize the foundation and the pier size, but we've got a very wide box, so we're trying to focus those loads inward as much as possible, going up to the maximum ratio of the cantilever wing length, using the maximum web slope to start transitioning those loads into the narrowest profile possible. That helps also minimize the cap size, though it doesn't look like it from this graphic with no architectural treatment, but it could be a lot worse. Another substructure consideration is using single piers or twin wall piers. I like twin wall piers a lot. They provide a very stable platform to erect your cantilever because they basically form a compression and tension couple. And as long as you keep the space between them, between 20 to 24, with 20 being optimal, you should not have uplift given the vertical downward load versus the couple from the out of balance that should balance each other out. You get much thinner together, then you can have uplift during construction. And that's not good. You're going to end up having to require tie downs or something else. If you don't use twin wall piers as a platform during construction, you're typically going to need to, unless you have a really, really stout single pier, you're going to need to have some struts or temporary piers on one side or the other or both. That adds costs. There may be a separate foundation required from it. So I like to include it in the structure as a whole as a twin wall pier where possible. The other aspect I like about twin wall piers is that they can be very flexible because there's not a lot of bending induced in them in the cantilever state because it's all handled as a couple, compression and tension in the two twin wall piers. So when you get in a continuous state, you have longitudinal movements due to creep and shrinkage of concrete, temperature rise and fall. Most piers are very flexible. They can accommodate it without inducing extra force into the foundations, or I should say minimize the force. Obviously, some forces that need to be accounted for. If we had a single pier stout enough to erect the balance cantilever, it's going to be very, very stiff and very, very problematic to accommodate the movements without sliding bearings or some other means of doing it. If it were made monolithic, you're kicking enormous loads into your foundations. So consider using twin wall piers. Touch upon constructability. A lot of this is going to be focused on a precast casting cell, but the same principles apply if you have a cast in place structure with form travelers. The form travelers are holding up a casting system that's very similar to precast. And segmental economy is based, at least in precast, on casting one segment per cell per day. Now, if it's cast in place, it'll be about 1 every 3 days. But repetition, repetition, repetition to make this happen. You want to minimize operations. Therefore, you need to keep as many section dimensions constant as possible. And you want to minimize casting operations when detailing variable dimensions. In the United States, it's the labor costs that are driving our bridge costs predominantly, and a little bit of extra material to minimize the amount of labor can be a big advantage. Therefore, we want to minimize modifications to the casting cell. Now, this is a typical casting cell. I believe this is the Forebears Bridge, actually. And in the interior of this single cell box, you see what we term the core form. Underneath the bottom slab or the bottom soffit is the soffit form and the buildup to it, and term the soffit table. To either side, you have the outside web and wing forms. You can see that they rotate outward and pull outward slightly and rotate down to facilitate stripping. Not shown here, but what forms that face of the segment, at least on the back side of this segment, is the bulkhead. It's a metal bulkhead that forms the shear keys and so on. This side was formed by a match cast segment that just got removed and went to storage. So to review graphically, the core form is shown in light blue, the soffit form, soffit table, if you will, in red, the web and wing form in green, and wasn't shown or obvious in that other picture was the transverse bulkhead shown in yellow. So handling variations in segment dimensions, 2 general rules. One is to maintain the core dimensions that you can see outlined on this graphic. Basically the top slab between the webs as well as that knuckle region. If you can keep that constant, you're going to help a lot with constructability, and also maintain a constant web slope, another good rule of thumb. So how do we handle variable width? We can vary the cantilever wing length, and it's pretty simple. That transverse bulkhead just moves in or out. The wing forms will typically be manufactured already to handle the maximum length of cantilever wing. So you're just moving that bulkhead in and out. It can be done by 2 workers in a matter of less than an hour. If you try to vary that interior transverse span, you're going to be changing your bulkhead. You're going to be changing your core form. You're going to be moving the web and wing forms out, changing the soffit table, basically changing out the whole casting cell, and it becomes much, much more difficult to handle. So if you can, try and handle it in varying your cantilever wing lengths. Another thing we come up with as far as variable dimensions, how to handle variable crown points. Maybe we have a shoulder that's at a set cross slope, but then we have super elevation changing as the box goes through a curve. So if we can locate that variable crown point in the cantilever wing, as we can see on the left of this graphic, it's pretty easy. You can rotate the wing form down. It's going to obviously require some modification to the bulkhead, but that's pretty easy to accommodate, all things considered. If the variable crown point is between the webs, it gets a little more complicated. But if you can try to vary only the bulkhead and leave the core form alone, as shown on the right here, remember that we can rotate this entire box as a rigid body to accommodate the final required cross slopes also. So if you can accommodate it by just thickening the slabs a little or thinning them up within reason, it's going to work very well. Obviously, that falls apart as your elements get too much thicker, and you're going to have to bite the bullet and do something different. Having variable bottom slab thickness, thicken to the inside. It's kind of hard to see, it's on the left, but you can see a dotted line where the top of the bottom slab was, and that's going to obviously require a new bulkhead piece at the bottom, as well as modifications to the core form. Typically, there will be panels that just bolt onto the core form to form the variable overall depths in the core there. If you thicken to the outside, you can see in that case that the core form remains the same, but you're going to modify the soffit form. And typically there's little cantilever wings, if you will, that bolt onto the soffit form that accommodate the variable width due to the sloped webs. So either way has about the same amount of effort. I will mention again, keep the variation the same at all locations where it's needed, as we talked about in our practical example. I worked on helping produce shop drawings for a bridge which had been designed by someone else, where they optimized the amount of material required different at every pier, and that required just tons of modifications to the casting form, and then the workers trying to keep track of that and not make any casting errors. Very onerous. Again, a little bit of extra material to make things simple. True variable depth, we can see in dotted lines here where the minimum depth section was. We're starting to get variable depth. We're thickening the bottom slab also. It's going to require, obviously, new panels on the bottom of your core form, new pieces on the soffit form to bring it inward, obviously new bulkhead pieces to extend it downward and the thickness. The web and wing forms are typically manufactured with the maximum depth required automatically, so not a whole lot going on there. So you're requiring modification to 3 components. But if you have to do it for a longer span, you have to do it. And in my experience, it's still quite easy to cast 1 segment per casting cell per day. Variable web slope might help minimize changes to the soffit form, but it's not advised. It would require, since you have a different web angle, different joints, it would require warping of the web form. The form would have to be made flexible enough to achieve that warping. And we'd like our forms stiff for obvious reasons of concrete placement. And in my experience, you'll be fighting it in the casting yard, trying to close up your forms. It becomes really kind of a pain to work with. Touch upon aesthetics. Won't get into it too much. Aesthetics is in the eye of the beholder. But I will mention that at least I believe that box girders are inherently aesthetic, whether it's variable depth shown on the Winona Bridge to the left, the Moab Bridge out in Utah in the center, or whether it's constant depth on the Susquehanna River Bridge you can see on the right there. I think they look very clean and very aesthetic. So there's not a whole lot of reason, in my opinion, to make significant costly changes to commonly utilized cross sections. There's some minor modifications you can make, angular fillets and corners to match hard surroundings and pier shapes. For instance, the Hanging Lake Viaduct in Glenwood Canyon, the canyon had horizontal strata of limestone in the formation, so I wanted to match those horizontal hard lines. You can use rounded fillets and corners to soften the box a little. You do it to the extent shown here, it's not really that big of a deal. This is the Allegheny River Bridge showing angular soffits and corners. And this is the Leroy Selman Expressway that went to an extreme in rounding it out to soften it. Personally, I would not take it to that extreme, make it a little more subtle. Again, focus a little more on constructability. But the rounding gives certainly a nice appearance to the bridge. One of the issues with the aesthetics is our structure depths, especially for urban viaducts. We're very close to the ground, maybe just have minimum clearance underneath. They tend to look massive from the ground. So there's a number of things you can do to help combat that visual appearance. One is to use long cantilever wings so that the webs retreat into the shadows. A thicker bottom slab, the eye doesn't interpret that thickening of the bottom slab so much as a structure depth as if it was all in the web. Highly sloped webs, in my opinion, also tend to minimize the apparent depth to the eye. One of the big things we can do is with our railings. If you have a solid railing, the eye interprets the railing and the bridge together as the structure does, even though we know the railing doesn't have a structural function as far as the longitudinal and transverse design, except for impact loads, obviously, but it's not a structural element as far as the longitudinal design goes. If we can use open railing, then we can minimize that apparent depth because you don't see that solid thing and things look a lot better. Another thing you can do is to use a coping on the edge of your box. This helps hide segment joints and gives you a very smooth line that you can achieve. There is obviously some cost to it there. Slip forming is pretty much out, I would believe. And even forming this in the conventional manner with that coping is more difficult than if it were all on the deck. Slide says it protects anchors, also has a minor effect in that. In modern post-tensioning, we already have multiple layers of protection. The grout, plastic cap, pour back, so doing it just for the purpose of protecting anchors probably isn't warranted in these modern post-tensioning systems we use. Whoops, oh man, sorry about that. It's gonna be hard. I'm gonna have to go all the way down to the end. So as a person that I admire, very smart person, Albert Einstein said, everything should be made as simple as possible. If you're having trouble describing your design in the drawings, specifications, it's probably too complicated. We want things to be easily constructible. On the other hand, sometimes we have to do what we have to do. Variable depth structures, other project requirements. So everything should be made as simple as possible, but not simpler. Not simpler as that required to achieve your project requirements. So final word is keep it as simple as you can. And that ends my presentation. I thank you for your time. And there should be some time for some questions, I believe. Wade?
Yeah, that's great. Thank you, Kent. Excellent presentation. Very information dense. There's a lot to digest here. And so I encourage people to take another look at this in the near future and go through each of these slides very carefully. But no, very, very much appreciated. Thank you. We've got time for a few questions. We've got a few here. So I'm just going to start with the first one. Move my window up so I can read it. So I guess the assumption here is that these rules of thumb and guidelines are applicable to sort of the AASHTO design code. What are your thoughts on the applicability to perhaps the Canadian Highway Bridge Design Code or even the Euro Code?
I think generally they're going to apply well. If you follow these rules of thumb, it's going to work out fairly well. Your live load is typically slightly heavier, I believe, in the other codes, so you need to account for that. But other than that, these rule of thumbs, I think are going to put you in the ballpark.
Yeah, they're sort of first principles based, right?
Right, exactly.
Yeah. And then what about for, say, light rail transit? I think you mentioned that in a couple of spots, but and of course the picture on the screen here is a light rail transit structure. What are your thoughts on the applicability for that?
I think the overall span to depth ratios, the applicability is quite good. Your top slab might be the only case where you're looking at it a little heavier. Again, you've got heavier live load. The amount of post tension you have is going to be increased, but we really didn't talk about size and post tensioning. But I think it's generally applicable. The span to depths work out. The only caution is you might want to look at the web thickness a little tighter and err on that high side of that ratio. since the live load is for light rails typically 2.5 times AASHTO live load, at least on a per lane basis.
Okay, great. Is there a good way, a good rule of thumb for coming up with a preliminary weight for perhaps a form traveler or perhaps erection equipment for a precast cantilever bridge? Maybe a percentage of the heaviest segment or something like that?
I use something even simpler. Is I use for a form traveler 100 kips per web. And so obviously you have a 2-web box, you would look at a 200 kip form traveler, 3-web box, you're up around 300 kips. Pretty simple, but it's going to get you in the ballpark. So that's what I use. Beam and winch, slightly lighter, but the same principle applies. And if you have a ground-based crane, it really doesn't matter. Of course, we're required to put 10 PSF distributed construction live load to account for all the stuff the contractors like to put on the deck during construction.
Okay, great. And are these recommendations and rules of thumb really applicable to a box with 2 webs, or could you adapt that to perhaps a 3-web box or even wider?
Oh, yeah, they're absolutely adaptable. So when you're determining the total, for instance, the web width, we showed one with 2. So we calculated the total web width, and then we divided by 2 to get to 1 web. You get the total web width, divide by 3 to get to a single web width. With a bit of a caveat, not all webs between exterior and interior carry equal amounts of shear. So for instance, typically the total web width will be about 30%, 40%, 30% for your exterior, interior, exterior web. Your deck ratios, the length of your cantilever wing, again, a ratio of the interior span. If you have 2 interior spans, you just work on those ratios the same way. But yes, generally, I would say everything applies as long as you adapt it to the 3-web situation.
And do you have a rule of thumb or a recommendation for when you might start switching to a 3-web box from a 2-web box?
Oh, that's an interesting one. You know, you go back 30 years ago and pretty much as you started advancing beyond 60 feet, you started thinking about a 3-web box. But in today's world, I think it's more upwards of 70 or 75 feet or something like that. Single web boxes have been cast. And beyond that, you're probably definitely looking as you're up around 75, 80 feet on a 3-web box. Also, precast versus cast in place. I do not like precast 3-web boxes. It's really hard in storage, transportation, and erection to maintain that concept of a rigid body. It works much better in form travelers. So I'm going to do everything possible to use a 2-web box in a precast solution.
Yeah, okay, good to know. When you were talking about the variation of the depth for a variable depth box girder, you talked about using that Intrados curve, and there have been some bridges that have been done where the variation in the depth was handled with a linear variation along the length of the span versus a curve like this. What are your thoughts on the advantages and disadvantages to either one of those?
Well, a linear variation, in my opinion, you end up with too much concrete out there in the cantilever state versus a curve that thins it up quicker. So it's going to be more onerous on, you know, your bottom slab thicknesses to handle negative moment as well as your cantilever post-tensioning. In either case, as far as casting the segment, you're going to modify the same amounts of the formwork. You know, for a true variable depth, you're going to be modifying the soffit table, the bulkhead, and the core form, whether it's linear or curved. So in my mind, I would always go curved for these long span bridges, where it's true variable depth. The exception is if we have a minor thickening in what would otherwise be a constant depth structure, or keeping the core form the same, again, upwards of 250 feet or so. These are typically done linearly because you're not trying to emphasize the curve overall in the span. So again, in my opinion, I think much more optimized to go with the curve than a linear.
Yeah, it's an interesting point. It sort of looks easier on paper because it's a linear variation, but in the real world, you're still having to vary the depth of the casting cell each segment, and you're still, within the length of the segment, it's still a chord from one end of the segment to the other in terms of that slope. So
right.
really,
So
there's no advantage in detailing the rebar either. So
right, it's exactly the same. It's just what it looks like and the consequences. And if it's linear from the pier to the center of the span, it's a lot of concrete you're supporting, out there versus if you thin it up faster with an exponent greater than 1.
all right, and then one more question here about the twin wall piers. Good discussion on that. Would it be possible or advantageous to perhaps have a mix of twin wall and single column piers on a project or on a bridge or within a unit?
Yes, that's possible. One case that comes to mind is the 4th Street Bridge, where we had used twin wall piers. We had a single long span over a rail yard. And then as we got to the side spans, they were much shorter, and they were actually, the end spans were actually cast on false work, and the cantilevers met out, not at the span length itself, but partway in between. And a combination of twin wall and single piers worked well. The twin walls were monolithic, the single piers had bearings. It was fairly close to the ground, but yeah, there's no reason you can't mix and match given your project constraints.
Okay, great. Well, that wraps it up for questions for today. Kent, once again, thank you very much for an excellent presentation. And Greg, I'll turn it back over to you.
Yes, thank you. And again, Kent, thank you for your presentation. And again, my apologies for the little burble we had at the beginning of the presentation. If I'd encourage you to, if you didn't register for all of our webinars, the QR code on screen will let you do that, or you can go to our website, and certainly you can continue to register for each webinar independently. You'll get a certificate of attendance here in about a week, and in the next few days, we will be posting a PDF copy of the slides, including the slides maybe that you missed, as well as a link to a recording from today's presentation if you want to go back and revisit that. So with that, I will again thank Kent Montgomery for his presentation and certainly for his tenure with ASBI and as our committee chair. And I know you look forward to retirement, but certainly there are a number of us who are sad to see you go and hope you will continue to stay in touch with the industry. So with that, we'll sign off. So thank you, everybody.